Okay, so this is the second lesson that we've done on networks and graphs. And just a reminder of some of the basic stuff that we did yesterday is that a network is a series of vertices that are connected by edges. So I just want you to keep that in mind as we're sort of going through this next bit. So what we've got here is we've got an undirected graph. So the order doesn't matter. So if I'm looking at this area at the moment right now, what we've got is we've got four vertices there, A, B, C, and D, and then they're connected by four edges. This particular one is what we're calling a planar graph. Now, it's a new term that I'm introducing now. So a planar graph is a graph that has no edges that are crossing over. Now, if we move across to this one here, you can see that there is a crossover. So that line that goes between C and D crosses over with the line that goes from A to D. However, this can actually become a planar graph by redrawing it. And there's actually two ways we could do it. We can actually move this edge here so that it then comes around the back like that. Or we can move the other line and move it around the back of this one. And we've got, if you look over at these two examples over here as well, we've got two examples of the same graph that has been redrawn with no crossing lines. Now the key point here is that there still needs to be the same lines between the same vertices. But they can be redrawn so there is no crossing. So that's I guess the key premise of what we're talking about today. So I suggest you just spend a couple of minutes just putting down the basics of what I've just discussed and also what's on this slide, and then when you're ready, hit play again. Okay, so the next key bit of information when we're talking about planar graphs is when we're talking about regions. So I'd like you to have a look at this network down here, and it's a series of 5 vertices and a whole bunch of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Now, a region is an area that is bound by edges. So we've sort of labeled them here. 1, for example, is in an area that it can't get out of because it is bound by, in this case, 3 different edges. But if we then have a look at this one down below, number 2, it is bound by 2 edges, but nonetheless it's inside and it's contained between edges. So this particular network has 5 that are regions that are inside the graph. However, in addition to those that are bound by edges, there is actually a 6th one, which is the region that's outside. So key bit of information is that there are 5 internal regions and 1 outside. So we would say that this particular graph has 6 regions. I suggest you make a note of that as well. Now, when we are talking about regions, vertices and edges, there is actually a rule that applies, but I guess we'd like you guys to have a go at trying to discover that. So looking at this one here, could you please take the time to, for the boxes over on the right hand side, write down the number of vertices there are, regions and edges, and then do a calculations of vertices plus regions take away edges. Once you've done that, I'd like you to do the same for this particular graph and just see what you discover. Key thing here is when we're talking about this, whoops, that one there, even though it counts as 2 in terms of degrees, it is still only 1 edge. So just be careful with that one. So just take the time to count the number of vertices, regions and edges for both of these, then do the calculation and just see what you discover. Okay, so I'll just do this top one first. So the number of vertices, how many dots are there? There are 5. How many regions are we dealing with? The 5 inside plus the 1 outside means 6, and edges 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if I just do a quick calculation there, I get 5 plus 6, which is 11, take away the 9, and I'll get an answer of 2. Okay, now, as it stands right now, that doesn't mean much, but we're hoping that that'll actually come together and form part of our rule. So if we do this one down the bottom, vertices are 1, 2, 3, 4, 5, 6. Oopsie daisy. 6. Number of regions, now 1, 2, 3, 4, and 5, plus this one outside. So that means we end up with 6 of those as well. And then edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if we do the same calculation, 6 plus 6 equals 12, take away 10 equals 2. So we've ended up with 2 for both of those calculations. Now, if I move on to the next one, what you guys have hopefully discovered is that we've found Euler's rule. So, for any planar connected graph, so we've been talking about planar graphs, these are the ones that have got no crossovers, the rule should be the same. If we add together the vertices and regions, take away the edges, then we should get an answer of 2 every single time. So you'll get an opportunity to do some more work with Euler's rule and with some other graphs as part of the work that we're going to set later. We're just going to cover one last rule that I guess we'd like you guys to discover as well. On the board at the moment, there are 3 planar connected graphs. They've got different number of vertices, edges, and regions. But this is about really analysing degrees. So we haven't talked much about degrees in this lesson. Remember that degree is the number of edges that go into a vertice. So just a little bit of a revision. This one up here is a degree of 3 because there are 3 different edges that go into that particular vertice. Let's take this off. While C, the one below it, just here, it's only got 1. So that would be a degree of 1. What I would like you guys to do is to spend just a few minutes to fill in this table at the bottom. And what I'd like you to do is just to write down the degree of each of the vertices. So, for example, for graph 1, degree of A, we just did that one, was 3. In graph 1, the degree of B is 2. So I'd like you to go through and do all of those. Should only take a couple of minutes. Just pause the tape and then we'll go on in a minute. Okay, so I'm just going to go through the answers here. So C1 and D2, and then we don't have one of those. I'll just colour that in there. For number 2, A's just got 1, B has got 1, C has got 2, D has got 3, and E has got 1. And we go up to this other one here. A has got 1, oopsie daisy, 3, C has got 3 as well, and D has got 2, sorry, and E has got 1. Now, I guess I'd like you to see if you can see any relationship between these numbers. It actually is quite tricky. So the rule for this particular one, and you've sort of got to get your head around this, is as follows. For any connected planar graph, there are always an even number of odd degree vertices. So if I then come back here, how many odd degrees are there in graph 1? Well, there's 1, there's 2. So just change colours here. There are 2 odd degree vertices. I'll put a 2 there. How many are there in graph 2? There's 1, there's 2, there's 3, there's 4. So there's 4 odd degree vertices, and if I do the last one, 1, 2, 3, there's 4 there as well. Now, all of these numbers down the bottom, 2, 4, and 4, are even numbers. So again, make sure you make a note of this, but there are always an even number of odd degree vertices for a connected planar graph. Now, there's some work there that is based on the learning from this video. Suggestion is that you hop into that and have a go at those particular questions.